Okay guys, welcome back. This is the second part of L22. We have one theorem and one example to go through. Theorem 10.9, equidistant chords theorem. It says, in the same circle, or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so in this diagram, we have circle E. So let's go ahead and recreate this. So go ahead and draw these notes along with me, please. Okay, let's start off with just kind of freehand a circle. Make it nice and big. We'll draw the center. We're going to label the center E. Okay, and in the circle we have two chords. Okay, and these are not special in any way. They don't hit the center. They're not diameters. Okay, we have one chord over here. And we're going to label this chord segment AB. Okay, so there's AB. And before we draw the second chord, I want you to remember our definition of the distance from a point to a line, or the distance from a point to a line segment. If I ask you, hey, how far is E from this line segment? Remember, there's infinitely many ways that we can get from E to the line segment. But the distance from E to segment AB is the shortest distance, which is also the perpendicular distance. So if you're starting at E, and we want to know how far is it from E to AB, we want to go perpendicular. Okay, so let's go ahead and add that little perpendicular in right now. Okay, I'm going to use black. Okay, I'm going to pretend that's perpendicular. Okay, let's say that that's perpendicular. And let's call this point F. Okay, so how far is segment AB to the center? It is this length from E to F. Okay, it's the length of segment EF. Okay, so now let's go ahead and draw the second segment. Let's say there's another segment inside of this circle. Okay, and it's over here. This segment, let's go ahead and call this segment CD. Okay, and we want to know, well, how far is segment CD from point E? We have to do the same thing, right? We have to go perpendicular, okay, from E to segment CD. And let's go ahead and label that point G. Okay, so now what we know is that segment AB, okay, if this is congruent to segment CD, then we can conclude that EF is equal to EG. Okay. And the opposite, the converse, is true also. If we find out that EF and EG are the same length, if these two are equal to each other, then we know that these two chords are congruent segments. Okay, so let's go ahead and apply that to our example. Okay, so this is a little bit of a complex example. Okay, but we have to apply the theorem we just learned and then do some more work as well. Okay, so in the diagram, we're given that QR equals ST equals 16. So QR, this chord, is 16. Okay, we also know that ST, segment ST, okay, its length is also 16. Okay, and what we want to know is find the radius of circle C. Now if you look at this, okay, there's a radius here, CW, there's a radius here, CX, but we're not going to use either one of those. We're going to draw in our own radius in just a moment. Okay, and we're going to use what we know about right triangles to use some right triangle geometry. Okay, so first of all, we also know that CU, this little piece right here, is equal to 2x, and CV is equal to 5x minus 9. Okay, well, let's start using the theorem first of all. So we know that QR is equal to ST. So these are two congruent chords in the same circle. So if you have two chords that are congruent, then you know that their distances to the center, okay, this little piece, CU, okay, and this little piece, CV, the distances to the center are equal. Okay, so the first thing we want to do is find out, well, how long is that distance? Okay, so we know that CV, or CU, equals CV. okay, and that is because of the theorem. So let's substitute in their actual lengths. So we know that 2x is equal to 5x minus 9. Okay, let's go ahead and subtract 5x from both sides. So we get negative 3x equals negative 9. Let's divide by negative 3, and we get x equals 3. Okay, substituting that value back in, let's substitute it into the short one, the easier one, 2x. Okay, we see that cu is equal to 2 times 3. We can just do the mental math on that. That's 6 units. Okay, and that is also how long CV is. Okay, so I'm just going to write 6 right there. Okay, so this little piece right here is 6. We also were given up here that QR is equal to ST is equal to 16. So QR, this entire thing is 16. And if you look at this, this is a diameter. WX, segment WX, is a diameter. And we know that the diameter is a perpendicular bisector of this chord, right? And because it's a perpendicular bisector, we know that these two pieces are congruent, meaning their lengths are equal to each other. So if this entire thing is 16, and this diameter is bisecting it, this must be 8. So let's go ahead and write in 8 there. Now we're going to go ahead and draw in the radius. I'm going to pause a moment and see, can you figure out where the radius is that we're going to draw? And when we draw this radius, we're going to use what we know about right triangles. Okay, so where would we draw a radius that will help us solve this problem? Okay, so hopefully you figured out that the radius is going to go from the center C over to Q. Okay, and here's a right angle, and what do we have? We have a right triangle. This is 6, and this is 8. This sounds a lot like a Pythagorean triple. You guessed it, this is a 3, 4, 5 Pythagorean triple. It is scaled up by a factor of 2. So this is 3 times 2, this is 4 times 2, so this would be 5 times 2, which is 10. Okay. So we know that CQ is equal to 10 units. So let's go back and answer the question, find the radius of circle C. Okay. The radius of circle C measures 10 units long. Okay, that's all for today. If you need any help with the homework, please post, or if you have any questions, please post your comments as public comments in Google Classroom. Otherwise, you can always email me or email your teacher. And good luck with your homework, and we'll see you in the next video.